Okay, so we'd like to prove this theorem on antiderivatives. We're told that if f is an antiderivative of little f of x, then capital G of x is also an antiderivative of f of x if and only if g of x is equal to f of x plus c, where c is a constant. Okay, so now, to prove this is a two-directional proof, so we have to prove that if g of x is an antiderivative, then it must look like that. It must differ from f by a constant. That's what that's really saying. And then the second way is if g of x does look like that, then we want to show that f, or that g is in fact an antiderivative. So we begin by making the assumption, we're going to go the easy way first. Let's assume that g of x is in fact some function of the form f of x plus a number. Well, then we can go through and differentiate both sides. Then we get g prime is equal to f of x, f prime of x. But f prime of x is equal to f of x, and why is that so? Well, that's because f was assumed to be an antiderivative, and if it's an antiderivative, when you differentiate it, you get little f of x. So we get our result that g is in fact an antiderivative of little f. So now we begin to prove the other way. So we say let g be an antiderivative of f. Of course, what that means is that g prime is going to be equal to little f of x. And we begin to do so. Okay. So now recall, of course, that f prime is also little f of x as well. And so what we're going to do is a common technique here in calculus and proofs with calculus is we create a new function. So we say let h of x be equal to f of x plus g of x, minus g of x, sorry. We could also do g of x minus f of x, either way. Now pick any a and b in whatever interval that these happen to be antiderivatives on. And while we're at it, let's assume that a is less than b. Now, h is continuous over that whole interval. Why is it continuous? Well, because both f and g are continuous. How do we know that f and g are continuous? Because f and g are differentiable functions. And a result from a long time ago, we didn't make a big deal out of it, was that if a function is differentiable, it's also continuous. So of course, since they're antiderivatives, they're also differentiable on that interval. Now we're moving through this fairly quickly. If at any point in time you do need to pause, please do so. To kind of catch up and think about these problems. So we know that h is continuous and differentiable on the interval. Well, how does that help us? Well, we happen to have a theorem that talks about a function that's continuous and differentiable on an interval. And so that theorem was the mean value theorem. We know that there has to exist a point somewhere in that interval, a c in the interval ab, such that h prime of c is equal to h of b minus h of a over b minus a. That's the mean value theorem. So we know what h prime is, though. H was f minus g, so h prime is f prime minus g prime. But f prime is little f, and g prime is little g. So, I'm sorry, it should actually not say little g. That should say f. I apologize for that error there. It should be f of x minus f of x, and of course that result is 0. So h prime of c is 0. Why is it 0? Because h prime is always 0. H prime is always 0. And so now, by the mean value theorem, we know that h of b minus h of a, excuse me for just a sec. So we have h of b minus h of a over b minus a has to be equal to 0. And so if that's the case, since b and a are not equal, they're not 0, we can multiply by b minus a and get h of b minus h of a equals 0. But if h of b minus h of a is 0, then h of b has to be equal to h of a. Now that was true for any ab in the interval. We pick any random ab. So it's in fact true for all points in the interval. They're all equal. Well, if they're all equal, then h of x has to be equal to some constant. Call it c. And so finally we have c is equal to f of x minus g of x. And so from there we have g of x is equal to f of x plus a negative c. But whether it's c or negative c, it's still just a constant. And so we then have our result. And so we have our result. G of x has now been shown to be f of x plus a constant. So let me just real quickly fix that little typo. I would have fixed it earlier, but in the mode I'm in right now, it's just replaying stuff I've written before. And so if I went in and changed it, I think there's a fair chance that it would have messed up the whole recording. So again, instead of f of x minus g of x, that should have been f of x minus f of x. And again, that's why that's 0. So then we have our result, which establishes this theorem on antiderivatives. If f is an antiderivative, then the only way something else can be an antiderivative if it can be written in the form f of x plus some number. In other words, two antiderivatives differ only by a constant.